Hi, I'm Zor. Welcome to Unizor Education. We continue talking about physics. The course is Physics Plus. Plus means that it's just a little bit above maybe the regular high school level. So it's all part of the unizor.com website, and the website contains other courses as well. Math for Teens, for example, and Math Plus. It also has some lectures about relativity, theory of relativity, and some others. Okay, so we were talking in previous lectures of Physics Plus course. We were talking about certain laws of conservation, and today's lecture it's a lecture, it's not a problem solving. Problem solving will be the next one. So it's the lecture about one of the conservation law. Angular momentum conservation, or rotational momentum conservation. Okay, so here it is. First of all, we are talking about the force field, which means that in our three-dimensional world, at every point there is some force which basically acts on something, on some objects. Obvious example is gravitation force. Now we all live in the gravitation field of the planet Earth. At any point we do have experienced this field force, which goes straight down to the center of the Earth in ideal situation. So this is an example of the field, and in particular I'm talking about central field. So the central field, like gravitation, is characterized by very simple axioms. Axiom number one: the direction of the field at any point and magnitude are actually kind of supposed to satisfy certain rules. First of all, direction, it should be collinear with vector OA. So A is a point in our three-dimensional world. So OA is a vector from the center of the coordinate system, and we assume obviously that there is some coordinate system, inertial coordinate system, as we usually consider. So OA is a vector from center of the coordinate system to the point where the force is measured. So if this is our coordinate system, O, A, now X, Y, Z. So this is the vector OA. So the force must be collinear with this vector, so it's along the same direction. So that's one axiom. The second axiom is, if you have 2 points and the distance from the center is the same, so the distance is the same, then the magnitudes of the forces also should be the same. So both forces must have the same magnitude if it's on the same radius from the center. So that's very important. And also the direction should be either in or out for both of them. So they either go both towards center or both outside from the center. So these are basically 2 axioms which are sufficient to basically define the central force field. Well, now obviously if you have for two points on the same radius, any other point on the same radius will also have exactly the same property. What it means is that on one hand, I will use the r as the vector from point 0 to any other point in the space. For example, OA or OB. So I'll use the general vector r. So if you have a vector r, then the force depends on this vector r to define its direction. And what else it depends on? Well, it depends on the radius itself. So if I will use the regular letter r without the arrow as the radius as a scalar, then I can put f at r times r as the expression for the vector. Now, for the vector of force. Now, why is this actually correct representation? Well, for obvious reason. It's supposed to be colinear r, and that's why I can put r with some multiplier. Now, what this multiplier depends upon? Well, it obviously depends on the radius, the length of the radius, because all the vectors, which are all the force vectors, which are measured at the points on the same radius, have the same magnitude. So this is basically the magnitude, not the magnitude of the vector, but the factor of magnitude between the vector of force and the vector of position, which is r. So it's this particular expression follows from this definition. And I would like you to probably concentrate a little bit more to kind of agree that this is the correct representation. So again, it gives me, because it's multiplier, scalar multiplier by r, it gives me collinearity, which is the first requirement for the central force field. And the fact that it depends only on the distance between 0 and the point, so basically it depends on the value, the magnitude of the vector r. That's what the distance is the magnitude of the vector of position. That's why I can put this way, where f is some function which is independent of r, obviously. I mean, f itself, the expression of the function. Like, for instance, if you have the gravitation force, usually we use for gravitation force what, m divided by some constant, whatever the constant is, divided by r squared, right? That's what we usually use for the Newton's law of gravitation. Now, this expresses the magnitude of the force, not the direction. If I would like to express it as a vector, where direction is also involved, I can put it this way. I can multiply it by r as a vector and divide by its lengths, so it will be the third power. Now that would give me the unit vector along the direction r, and then the unit vector, which gives me just the direction, is multiplied by m times m divided by r squared, so it would be r cubed. So this is this is the expression of gravitation force, and this function is this function. And any other central force which satisfies these two requirements can be expressed in this particular form, something which depends only on the length of the radius to the point where the force is measured, times the position vector. Okay, now we know the expression of the force in this particular case, and we also should mention that if r is a position, then are, first derivative is vector of velocity, and the second derivative of this vector is the vector of acceleration. That we know from the regular physics mechanics course. So the first derivative of position is velocity, and the second one is the acceleration, which happens to be the first derivative of the speed, right? Second derivative of the position is the first derivative of the speed, if we will differentiate both sides. All right, so keep this in mind. So this will be our kind of symbolics which we will use. Now we are going into angular momentum conservation law. Now we have to define what is angular momentum. Okay, in vector form, angular momentum is defined as, it's a vector. It's a vector product of position vector and momentum vector, where momentum vector is, as we know, is mass times velocity. Again, in one-dimensional case, we don't use the vector form, so mass times speed would be the momentum. But in the vector form, obviously, that's basically the same thing. Just use vectors, three-dimensional vectors, instead of one-dimensional case, usually considered in the regular high school course of physics. So this is the vector form of angular or rotational momentum. So again, two things are involved here. The radius as a vector actually, and the velocity. So if you have, let's say, the rotation around certain axis, radius would be towards the point on this trajectory, on the circle. The velocity would be tangential, so this would be my r, this would be my velocity. They are, in this particular case, perpendicular to each other. So what would be their vector product? Well, vector product would be perpendicular to both, so it should be along the axis, either down or up, depending on the direction of the v. Okay? So in this particular case, that would be L. So L is always along the axis of rotation, L as a vector. And obviously its magnitude is magnitude of this times magnitude of that times sine of angle between them. Remember what vector product is? The magnitude of vector product? It's magnitude of one times another times sine of angle between them. In this case, sine is of 90 degrees 1. So basically the momentum in this regular rotation would be just the multiplication of their lengths of these vectors. Okay, and now all I would like to prove is that this thing is constant wherever our object is moving within the central force field. The momentum, rotational momentum, would be preserved, would be constant. That's basically the theorem which I would like to prove today. That's the purpose of this particular lecture. That angular momentum is constant as long as the forces are central. Now, here is a little bit deviation from this. Let's just consider that the force field is not constant like gravitational field. But what if it's changing for whatever reason? Would that be exactly the same? Well, if the force is changing as the time goes on, at any particular time, the force will be central, as long as the force is central, even if it's changing within the time. As long as the force is central, the momentum would be preserved. That's very important thing. So again, I'm talking about central force, not only at a constant, not only always not changing with the time, but also if the central force is changing with the time, as long as it remains central. Well, in case of gravity, let's just imagine that we are orbiting around Sun. So the gravitation is basically caused by the mass of the Sun. But Sun is losing its mass because it's basically emits all the energy, and with the energy goes mass. So it's kind of changing in mass. Still, the angular momentum conservation law would still hold. That's what's very important, because at any given time it's central. So it used to be central and now it is central. The new force contributes to something but not into this particular expression. And how can I prove it? How can I prove that some function is constant? Well, I just have to differentiate it and see that the first derivative is equal to 0, right? Okay. So let's differentiate it. So the first derivative of vector product, it's basically similar to derivative of product of two functions. So it's r times p plus r derivative plus times p plus r times p derivative. This is the regular formula for differentiation of the product, in this case vector product of two different things. Alright, so let's just calculate what it is. Alright, so what is r derivative of the r? Well, derivative of the r is v. Okay, so L is equal to v, which is velocity, times p. What is p? P is m times v. Right? P is m times v. Plus r. Now this is supposed to be vector product. Vector product of derivative of p. Now p is m times derivative of v. Okay, now the derivative of v is a. So that's equal to, well, I can put m outside because it's a constant, it's a scalar. V times v plus, again, m out, R vector product A. Great. Now, let's talk about this. This is equal to, according to the Newton's law, mass times acceleration. Vector acceleration in this case, right? Okay, from which vector of acceleration is equal to f of r times r divided by mass. Okay, equals, what is v multiplied vector multiplied by v? These are one and the same vector. Vectors are collinear, so the sign of the angle between them is equal to 0. Its vector product of these two is equal to null vector. So it's a null vector. what is this? This is m times r multiplied by, vector multiplied by f of r over m r again. Again, this is the scalar. It goes out as the, and what we have r multiplied by r. Again, vector multiplication is 0. So this is 0 and this is 0, which means this is 0. So the first derivative of angular momentum is 0, which means it's constant. It does not depend on the time. As long as the forces are central, our angular momentum is preserved. So this is the law of conservation of angular momentum. Now, it's not a trick, obviously. I mean, with all these derivatives, which are somehow magically come to 0. It's all obviously follows from the very simple thing. If the force is central, it does not contribute to rotation. Only the tangential forces, which are not central, obviously, contribute to rotation. And angular momentum is kind of a measurement of the rotational kind of thing. That's what it's called, rotational momentum or angular momentum. So, as long as the force is central, it does not contribute to rotation. So, in this particular case, this thing is preserved, and that's the law of conservation. If r is changing somehow, for instance, sun becomes lighter, and it attracts the planets less than it used to be. Well, the planet can actually go, in this case, a little bit on a tangential trajectory and increase its radius and increase its space or decrease its space depending on where we're going, towards the sun or outside of the sun. So if sun is getting less massive, then the radius is increasing, so the linear speed should be decreasing on a greater distance. So the planet would be on a greater distance from the sun, and it would have a lesser linear speed. But then again, the equation would still, vector product of these two things, the position vector and velocity, would be the same. At the very end of this change, so to speak, the product would be between r and p would be the same. Or vice versa. If you're increasing, let's say, mass of, let's say, Earth, when some meteorite comes to Earth and increases its mass. Well, if the mass is increased, the gravitation is increased, so the moon would be attracted more towards the Earth. It would come closer. But to come closer, it should increase the speed to still stay on the orbit. And because, again, because the rotational momentum, angular momentum, would be preserved. Okay, that's it, basically. That's all I wanted to present to you in a regularly, strict, mathematically strict way. By the way, some other laws of conservation, for example, law of conservation of momentum, also can be derived just from the Newton's law. This is the Newton's law, which we kind of accept as an axiom in general mechanics. And from this, the law of conservation of regular momentum, which is mv, would also follow very easily. Okay, so I do suggest you to read the notes for this lecture, because every lecture has a note. Note is written as a textbook, basically, for this particular lecture. So it's all on unizor.com. In this particular case, you go to course called Physics Plus. The part is laws of Newton, and the central force is the lecture there. read the notes, just refresh your understanding of this whole thing, of this law of conservation of angular momentum. And if you wish, you can just have a piece of paper and try yourself to derive the law of conservation more or less the same way as I did. So don't forget that this is a vector product between position and the momentum, and everywhere else vectors are obviously used in this particular case because we're talking about rotation, which is definitely at least two-dimensional or even three-dimensional case. And I'm using this first derivative of position is velocity, and the second derivative is acceleration. All vectors. Okay, that's it for today. Thank you very much, and good luck.